Thank you everyone for coming to the seminar. I'd like to introduce Dr. Wencho Zhou. He is a professor in the Department of Mechanical Engineering at the University of Arkansas. He directs the AM³ Lab there in mechanical engineering. He graduated from Huazhong University of Science and Technology with a BS degree, Jiatong University with an MS degree, and Georgia Tech with a PhD, all in mechanical engineering. His research focus here is on scalable digital manufacturing technologies. He's the co-founder of CTO of AMBOTS Inc. It's a startup for commercializing the swarm 3D printing and assembly technology called SPA. Dr. Zhou is nationally and internationally recognized for his original research and contributions to manufacturing education, such as the 2019 Randy Stevens Scholarship, which is an annual teacher's award by Additive Manufacturing User Group, 2018 IET Innovation Awards, highly commended in manufacturing technology, the winner of the 2017 America Makes Additive Manufacturing Curricula Challenge, outstanding paper of 2017 from the Rapid Prototyping Journal, the 2016 Ralph E. Powell Junior Faculty Enhancement Award, and a highly commended award for the 2013-2014 Emerald Engineering Outstanding Doctoral Research Award in Additive Manufacturing category. He's also received the Best Presentation Award at the Solid Freeform Fabrication Symposium, Best Paper Award at the International Conference on Advanced Research in Virtual and Rapid Prototyping, and he has had worldwide media coverage. The title of his presentation that he will be giving today is From 3D Printing to Digital Manufacturing. Welcome, Dr. Zhou.
Well, great. Thank you so much for the introduction, and thank you so much for the opportunity to share some of the research I've been doing in the mechanical engineering department. Without further ado, let's get started. So we humans had a very humble beginning since tens of thousands of years ago. We live a very nomadic lifestyle with no stable food source and with no fixed residence. And then there was the first revolution, which was agriculture, which gives us the stable food source and fixed residence, and so that we can settle down to form communities and develop civilizations. And then the second revolution came, which was the industrial revolution. It provided us the power to mass produce and freed us from a lot of labor-intensive activities. The problem is that it's very capital-intensive, which is one of the reasons why capitalism was developed to raise money. And also, it sort of sacrifice our individuality in terms of the product that we can use. We're largely forced to use very similar products with each other. And then the third revolution came, which was a few decades ago, with personal computers. And personal computing democratized information. So nowadays, we all receive different information for ourselves with TikTok, Instagram, Facebook, etc. And you don't need that much of capital to develop companies. You can have a couple gigs to start companies in a dorm room, such as Facebook, etc. So if you look at timeline here, so in this nomadic lifestyle, we lived tens of thousands of years. And in agriculture society, we live for 2,000 years. And then in this industrial society, we lived about a few hundred years. And for personal computing, it was a few decades ago. So we're accelerating into the future. So which keeps us wondering what would be next. And so there's many different emerging technologies that could fundamentally change how we live in the future. such as AI, Internet of Things, blockchain, etc. So my opinion is the personal fabrication is going to take a fundamental need to change our lifestyles, and which can be made to an analogy can be made to personal computing, of how personal computing have changed us. And personal fabrication will give us, the freedom to go outside of this virtual 2D screen and bring this again in the virtual world into the real world. Not just for the products that we consume with 3D printers, but also for maybe the buildings we're living in, the food we consume. All these things can be digitally manufactured on demand at low cost. So speaking of manufacturing, if we take a look at the manufacturing technology history, and in the very beginning, most of the production is carried out by craftsmen, and who uses general purpose tools. And for example, we go to tailors for our clothes, we go to shoemakers for making our shoes. And so there is a constant trade-off between the product variety and the product volume. So in the age of craftsmen, we were able to get a very customized, individualized product, and the product variety is, very large. And in the meantime, you can't serve that many people because the productivity is low. So in order to increase the production volume, and we usher in the age of mass production, symbolized by the first implementation of the assembly line in 1913 by Henry Ford. And with the driving force of individuality, everyone is different. We want different things. We don't want to use the same product as others. And the industry was forced to, adopt more flexible manufacturing lines, such that they can produce a wider variety of products. For example, you can buy Ford Focus, you can buy Ford Fusion, to increase the variety at the sacrifice of a slightly higher cost. And the limitation is that if we go more individualized, more customized, more personalized product, the cost is going to go higher. And the hope that we're putting on is the future manufacturing technology will be able to fabricate more personalized products at low cost. And so if we look at this curve here, it's almost going a full circle, and is that we're going to be able to get more personalized product with lower cost. So with the digital manufacturing revolution, where we are today, there's still a few roadblocks we have to overcome in order to get to the stage where we can have, on-demand digital manufacturing of personalized product at low cost. And one of that is printing quality with 3D printing at the center, and the second one is the cost. So there are many people who are working in the field of digital manufacturing or 3D printing that focusing on improving the printing quality. And so when I started my lab, I decided to take a different approach. I look at the cost issue here, trying to develop new technologies that can really bring down the cost so that this technology will become more accessible and being, getting into the hands of a more regular person. So this is why we established our primary mission as developing scalable 3D printing technologies. And by scalable, we mean go faster and larger and being faster is one of the primary goal, because manufacturing time determines essentially the price of a product, because everything is priced by time. And for example, if you injection mold a cup, it takes a couple of seconds to do that. But if you 3D print one, it will take a few hours, which will dramatically drive up the cost. So over the past years, we've been exploring 3 different approaches to bring down or bring up the manufacturing speed or printing speed. The first one is the Swarm 3D printing platform, and the second one is a new process called microheated array powder sintering, and the third one is Inkjet, which is what my PhD was working on. And we also dive into a little bit secondary mission to expand the applications of 3D printing by developing some new applications with high resolution 3D printing, and also printing of optics. So the first project is Swarm 3D printing, and the motivation was really looking at these individual 3D printers. I believe most people are familiar with it today. They are typically a standalone machine with these no-cost FDM printers, and with a single print head, single color, single materials, and also the print size is limited to the size of the printer. And most of the time, you're printing mechanical structures. So although there are ways that you can include multiple print heads, multiple colors, and multiple materials, and print larger, and also include other other materials, for example, food. But these are very rare and not very well integrated, and they're still standalone machines serving single purposes. So our idea was to think outside the box by literally taking the printer outside the box by putting them onto a mobile platform, and also inspired by nature, not just having individual mobile printers, but having a lot of them work together on a production floor. So this brings a lot of advantages. For example, you can have different manufacturing processes working together. You can have 3D printing. You can also have laser cutting, machining, and you can have you can print different colors with different robots. You can print different materials with different robots. Also, the size is a lot more scalable, and you can add more robots and more floor tiles to print large and print faster by cooperation. In addition, you can also include, pick and place robots such that you can include some pre-manufactured components, such as electronic components that can't be printed nowadays with the current 3D printing technology. You'll be able to build more sophisticated products in that way. And if you compare this Invasion platform, it literally brings the manufacturing into a new dimension. So in the current modern manufacturing, is still largely based on Henry Ford's assembly line idea, which is a 1D production line consisting of sequential machines to process materials step by step. And this is more of a 2D production floor where many robots can work in parallel, just like a swarm of bees working together to build beehives. So this is an early prototype that we built to exemplify the idea. And so you can see the logo here. It says AMBOTS. This is one of the companies that we started to commercialize this technology by with a suite of technologies we developed in AMBOTS, including mobile 3D printers, a wireless power mechanism, and a discretization method to divide the model into small pieces and assign to different robots, and also mobile gripper and wireless control of these robots. And so this is the first fully functional platform that we demonstrated with 2 mobile 3D printers that work together to print a very large mounting bracket. And this mounting bracket is first divided into 3 different pieces and assign it to 2 different robots. And these 2 robots will work together and to finish the printing and to print a piece that's larger than themselves to demonstrate the idea of cooperative 3D printing. And this video has gotten a lot of attention online with over 400,000 views on the internet. If you haven't seen it, now you've seen it. And so with just 2 robots, the scheduling, the planning of the production is quite simple, but the complexity rises quickly if you have more robots and have more production jobs. So in order to scale, we developed a mathematical framework to describe this problem and also a scaling strategy. So this shows how 4 robots can be used to print a rectangular bar that's been divided into 20 chunks. And with this scaling strategy, we use a dependency tree to construct, the execution process. So each of these numbers represent a chunk, and these arrows represent the dependencies. And so you start from here, and only after it's finished, you can print this chunk. And the chunks on the same row can be printed at the same time without these robots colliding into each other. So to validate this, we did a simulation. So this is a simulation of how 16 robots can be used to print together to finish printing the landscape of Arkansas. And this has shown a speed up of 11 times with 16 robots. So just like humans, we humans have different expertise in different areas. We also want the robots to have different expertise, and so that they can actually work together to build more sophisticated products. So instead of having a homogeneous swarm, we want to have a heterogeneous swarm. And so this is a simple demonstration of how 2 different types of robots can actually work together with a 3D printed robot and also pick and place robot that's picking up a step motor and place it into a printed box for putting in electromechanical devices. So this is the developer pick and place gripper or demonstrating the digital assembly idea. So in addition assembly, we also want to develop different print heads to support different processes and materials. And this is a print head that we developed for printing photopolymers. For some of you who might have known 3D printing with stereolithography, they use this laser to scan over into a resin tank to kill the resins. But that's not compatible with the swarm printing platform because it's open. You can have a resin tank embedded in the floor. So we developed this deposition method. You deposit the photopolymers onto the print bed, and then you kill them instantly with UV light to print photopolymer parts. And in addition to that, we also developed a print head that can print a soft gel, which is a ballistic gel. It's transparent, and you can actually adjust its recipe to control its hardness. By controlling the water concentration in the gel, you can make it as hard as a bone or as soft as your tissue, as soft as your skin. And this can, with the swarm approach, hopefully can be used to print human models for either pre-surgical planning purposes, medical education, etc. And also another attempt we made was to printing food. We do envision the future restaurants to be a restaurant with thousands of robots that can take orders from your cell phone with precisely customized nutrition to your own nutrition profile based on your health metrics. So one of the things about food is that it pretty much determines who we are, because what we eat. And most of the diseases today is somewhat food related. If we can precisely tune food, tune the nutrition inside the food to your own customized health profile, we should be able to reduce most of the food-related diseases. And one of the things with 3D printing is that you can precisely control what nutrition goes into your food and what goes into your body. So we've also been dabbling around with a few other materials for other type of industrial applications, such as electronic materials with copper tapes, carbon fiber tapes for industrial applications and metals. And we haven't done too much on this front yet. And in addition to that, we're also working on autonomous planning for these heterogeneous jobs and swarms, and also adaptive intelligence based on vision. And in addition to that, the cybersecurity can become a very important issue when all the manufacturing is online, and you need to be able to protect the process and also your design. So that's swarm 3D printing. And a second project we made was maps short for microheater array powder sintering. And the motivation was because selective laser sintering, which is a process that uses a laser to scan onto a powder bed to fuse these powder particles layer by layer to build 3D objects. And it has also been used to make food as well. And so this is one of the most popular industrial application, industrial 3D printing processes in aerospace, in the healthcare industry, etc. And one of the downsides of this is that it uses a laser, and which is a very slow process because you have to scan point by point. And so to mitigate this issue and speed up, we sort of were using a different energy source, which is an array of microheaters. So microheater is a tiny heater that's pretty much just like the stove in your kitchen, but 1,000 times smaller. And you can actually make these microheaters onto a single chip, silicon chip or glass chip, and on the substrate to make a large array of that. And you can individually activate these microheaters. And so one of the things about heat is that it doesn't travel very far. It's very localized energy source. So if you activate a microheater and put it very close to the part you want to heat, you will actually generate a heat pattern, which can be used to send these powder particles. So with this array of microheaters, you can print one layer at a time instead of one point at a time, which will be much faster. So these are some of the advantages of this process. First of all, it's very scalable, and you can make thousands of microheater elements on a single chip versus a single point laser. And the scalability, making 1,000 microheater isn't going to be more expensive than making a single one, because the process is going to be very similar. And it's on a single, chip. So with this MEMS fabrication approach, these printer heads can actually be made disposable. With if mass produced, it can be less than $1 per printer head, compared to lasers that can cost up to tens of thousands of dollars. And also lasers require a lot of maintenance, and it consumes a lot of energy too. With some of the plastic or metal printers, you can easily have a watt power, up to hundreds or even thousands of watts. But with each individual microheater, we're talking about 100 milliwatts to maintain a very high temperature. In addition to that, another part is the process control. What laser is an open loop control. It doesn't really know what temperature it is at, and it's just responsible for shooting out energy. And sometimes you give much more than what's needed. But micro heater is different. Micro heater is a sensor itself, so you can actually precisely control what temperature it is at, which will enable much more accurate manufacturing control. So this was a simple idea, and with that idea, we started to implement it or test the idea. So we designed a small scale 2x2 array of micro heaters on a glass substrate, and so this is how it can be scaled. But we only made 4 just to for the simplicity. And with that, we designed a package to put a micro heater on glass chip, and with conductive leads to connect to external circuits, and also extended leads for connecting to the packaging. And then we use a high deck for the fabrication, and so this is a simple photolithography process with deposition of titanium and platinum layers of micro heaters. And you have these micro heaters made, and in the same way you can deposit the conductive leads, which we were using gold. And so don't be concerned that this might be very expensive, because they're not. We're talking about a couple 100 nanometer thick of these materials. So they're using very, very small amount of platinum and gold. And so this is the die of the micro heater that we just made, with the micro heater in the center, with 4 micro heaters in the center. This is a glass substrate. And then in order to package it, we deposit additional copper leads on this side so that it can be connected to external package. So this is a PCB board that we designed to put a micro heater die on here, so that we can apply some conductive epoxy to connect to these micro heaters. And then we designed a control board so that we can actually program to control individual micro heaters with code, and to activate them and turn it off. And a Arduino Mega board was used to control the micro heaters through this customer design temperature control board. And so these are some of the testing results. And so as you can see, this is a testing of single micro heater heating, and this is the time axis. It's in millisecond time scale, and this is the temperature. Our target temperature is 600 C. And as we can see here, this is the temperature going up, overshooting a little bit, and then the closed loop control kicks in and bring it back to 600 C in a few milliseconds. And the power consumption, which is green line here, and you can maintain the 600 C degree temperature at 400 milliwatts here. And so one of the things about this time scale is that it's comparable or even better than the laser process, which is also on a millisecond time scale. And a millisecond is the thousandth of a second. It's very, very fast. And for our humans to respond to anything, it requires at least 600 milliseconds, unless your brain is wired differently. So we also did a cycling test, and as you can see here, the micro heater can be heated up to over 600 C and immediately cool down to room temperature and cycle over in millisecond time scale, just because the thermal mass of the micro heater is so small. So as soon as you turn it off, it will cool down immediately. It doesn't need any additional cooling mechanism. So instead of doing 3D printing, we decided to go for printing electronics to start. just because it's a single layer. You don't have to print multiple layers, which is simpler to do. And also flexible electronics is a very fast developing industry and field. So we developed a printer to conduct the printing tests with this printing stage and printer head mounted here, and the micro heater is mounted here. And so we put a layer of silver nanopaste. It's a screen printing silver nanopaste on a plastic film, and we put it underneath the micro heater, and we activate that and move the printing stage. And after it moves over, so we washed off these unsintered particles, and we're left with a printing line. And as you can see here, these are some of the SEM images of the printing line here, and you can see clear melting signs of these silver nanoparticles. So these silver nanoparticles melt at about 440 C, and our micro heater is operating at about 600 C. So there's a clear melting, and we did a comparison with some of the existing technology for printing electronics. One is screen printing, the other one is inkjet. So this is a non-digital method, this is a digital method. And both of them will require both printing and curing, which because the nanoparticles needs to be cured in a temperature oven in order to be conductive. So this is our first prototype of the MAPS technology, and compare printing a single A4 paper per seconds. For screen printing, you will take over 90 seconds. For inkjet, you will take a few hundred seconds. For MAPS, you will take about 30 seconds. And the printing quality, which is characterized by the bulk conductivity as a percentage of silver. And so these are some of the best reported results in the literature, and this is ours, and it's comparable. So one of the things to realize is that this MAPS prototype we developed is the first generation with some simulations, and we can show that we can speed up the printing process by another 10 times with MAPS, with some additional control mechanism, and hopefully even higher quality, which we haven't tested yet. So that is MAPS. And another project we've been working on was Inkjet. And as I mentioned before, Inkjet was what I was studying when I was a PhD student. And for those of you who are not familiar with Inkjet, you have inkjet printers, in your office, which is a 2D inkjet printer actually, and printing, photos or documents. And one of the things you probably realize is that if you have an inkjet printer, it prints slower than the laser printers. And so this is one of the reasons we want to increase the printing speed of inkjet. And for 3D printing, there's two different ways of doing inkjet printing. One is a direct deposition. You're directly printing the materials to form a layer, and by layer, you get 3D objects. The other one is you're printing binders into a powder bed, and then do some post-sintering of this sintered powder, these combined powders. And it can also be used to print patterns on food, but across all these different inkjet printing technologies, the key to the printing speed is this print head, and which consists of many nozzles, as you can see here, many nozzles, and each nozzle is spitting out droplets very fastly, and those droplets are either inks or materials, photopolymers, nanoparticle solutions, or binders, etc. So in the industry, there's two commonly used inkjet technique. And one is the thermal inkjet printing, which uses a micro heater, which heats up to 300 C. and to vaporize the ink into bubbles, and these bubbles will force liquid out to form a droplet. And so this printheads are typically very low cost, and it's most commonly used in the HP and Canon inkjet printers, and it's sensitive to ink chemistry, and the cost is lower. And another common inkjet printing method is piezoelectric jetting. So it uses a piezoelectric transducer to deform a membrane to eject a droplet on demand. And so this method is more commonly used in the industrial inkjet printers. For example, if you want to pattern the back cover of your cell phone, pattern the floor tiles in your home, or doing 3D printing, because it's less sensitive to the ink chemistry, and it's more reliable. And these printer heads typically needs to be replaced after a certain amount of time. And our focus is more on this piezo electric transducer printer, and just because it's more commonly used in the industry for industrial applications. So the way that it works is that you give a driving signal to a driver to deform. Whenever you give an electrical pulse to this piezoelectric transducer, you will deform, and the deformation will cause the droplet to be jetted out. And you give one pulse, it generates one droplet. So it's drop on demand. And in controlling the way that it goes to the substrate, you can print patterns. So one of the things about inkjet printing speed is that its speed is controlled by 3 factors. The first one is droplet size, and how large the droplet size is. The second is printing frequency, and the third is the number of nozzles that you have. So for droplet size, you can't really do too much to control that, because one of the advantages of inkjet is the resolution. So for example, for a 600 dpi resolution, you are talking about a 50 micron droplet size. Larger droplet size, the resolution will go down. So if you don't want to sacrifice your resolution, you need to maintain similar droplet size. So for the nozzle number, so which is the primary way the industry has been used to speed up inkjet, and HP actually has the HP Moore's law to increase the inkjet printing speed, and they double the printing speed, every 18 or 24 months. And primarily by doubling the number of nozzles in the printer, but there's only so much that you can pack the nozzles into a printer head. And because there's limited space there, you have nozzle has a certain size. And so the print head that has highest number of nozzles is around 70,000 number of nozzles, which is a lot of nozzles. But that's approaching a limit. You can't do that, much more nowadays. There's also the printing frequency, which is the primary way that we're going to control, trying to improve. So looking at the current inkjet printer here, this is an industrial inkjet printer here from Fujifilm, and you can print about at a deposition rate of about 500 cubic centimeters per hour. And for a similar size of injection molding machine, and you can inject out 15,000 cubic centimeters per hour. So this is for a apple-to-apple comparison for making similar things with comparable budget. And you can notice that the inkjet is 30 times or 100 times slower than injection molding machines. And this means if we want to be able to compete with traditional manufacturing, we need to be able to at least bring up the printing speed by 100 times. And this is one of the motivations for our project. And as you mentioned, the 3 factors, the amount of droplet size, and the number of nozzles, they have been done to a, you know, very limit. And the only way that's been left is the printing frequency. So we actually have started, you know, the printing frequency a few years ago, and we revealed that the printing frequency is actually fundamentally limited by the surface tension of the fluid, which is based on the scaling analysis here, where sigma is the surface tension, rho is density, and d is the nozzle size. So the thing about surface tension is that you cannot really increase it too much. And you know, other than mercury, water is probably the one that has the highest surface tension you can get. You can't get much higher, not even to mention order of magnitude difference. So that puts a limit on it. So our goal is that to say if there's a way that we can surpass this limit. And one of the things that we realize in this equation is that this d here is actually, you know, more related to the nozzle diameter instead of the droplet diameter. Although in modern inkjet printers, the nozzle diameter is you know, typically similar to the droplet diameter. So our idea is that can we use a smaller nozzle to produce a larger droplet? Because if we can do that, and we'll be able to pack more nozzles, we'll be able to get higher frequency. And so our hypothesis here is that we can use a multi-power signal, driving signal, to, you know, drive more liquid out in order to form a larger droplet size, and with smaller nozzles while maintaining, you know, very high frequency. So this is our central hypothesis. It's sort of one stone, three birds. You're hitting these three, you know, factors of printing speed at the same time. And so to test this idea, we first developed a numerical model to simulate this inkjet printing process. This is the nozzle, and this is how the fluid is flowing out to form a droplet. And we did a validation of this simulation by tracking how this droplet is formed and flying out with the flying distance with x1, x2, x3, and x4 change with time. And this is a simulation of how the droplet is being injected. You can say is actually satellite droplets that's formed. And so this is the validation of the experiment. So these solid lines are experiment for x1, x2, x3, x4, and these dashed lines are x1, x2, x3, x4. And you can see they actually match very well. And one of the most interesting things is that it captures the formation of these satellite droplets, which form in the middle of the ejection process. It agrees pretty well. So this gives us a foundation to further study this ejection process. So we use this validated numerical model to study two pulses, to see if we can actually generate a larger droplet size with two pulses at this, you know, a similar frequency or faster frequency. So this is a simulation that we did. After the first pulse, that already pushes a half a droplet out, and it's starting to lag off. Before it completely pinches off, we send a second signal to drive more liquid out, and such that these two can match together to form a larger droplet. And we took this idea to an extreme. Instead of we just using two pulses, we include, you know, as many as 40 pulses here, and to see if we can get, you know, even larger droplet and with smaller nozzles. So this is a simulation. We actually form a very long filament, and they actually break off lightly to form a large droplet and with multi-pulse. And so this is a benchmark comparison we did just to verify that we can indeed increase the printing speed. And with this simulation, this is a benchmark printer head we get from this industrial Fujifilm printer head. It was using a 36 micron nozzle size, and with a 28 picoliter droplet size, and it was ejecting about 20 kilohertz, which is agreeing with our theoretical prediction of a limit of printing frequency. So in our simulation, instead of using the 36 micron nozzle size with the 14 micron nozzle size, we're able to use multi-pulse to bump up the ejection frequency up to 160 kilohertz, which is about 8 times of the industrial standard. Of course, this is simulation. You can't really believe what's produced in a computer unless you can reproduce in the real world. So we decided to take on a challenge to build up experimental setup to see if this idea actually pans out in the real world. And so this is the experimental setup we designed, and with a circuit control to control the piezo and the nozzle and the liquid chamber. And we also have a high-speed camera to observe how this droplet is formed, and we built it. So this is a control circuit, and this is oscilloscope, this is a computer, this is a high-speed camera, and this is the light source, this is the piezo, and this is the nozzle, and this is some back chamber control of the back pressure. So in this workflow process, you first design some signal and in your computer and input into this control circuit and amplifier, and you can validate in the oscilloscope before you send it to the piezo, and you send it to the piezo, which will eject a droplet. So this is a video captured by this high-speed camera to show how these droplets form from this nozzle, and this provides a good tool for us to study how the droplets form and what parameters are important and how the driving powers is affecting the printing speed. So we did some experiments with a single pulse and multi-pulse. And so this is a single pulse, this is a multi-pulse with the signals corresponding here. And they are printing at the same frequency, but with multi-pulse, we're able to generate a much larger droplet size. It was 530 micron compared to 390 micron here. So there's still more work that needs to be done. We're developing a theoretical model to understand exactly the mechanism for increasing the droplet size and the printing speed, and which is near finished, and we haven't published that, so I haven't included that in the presentation here. So in addition to the Inkjet project and this, increasing the printing speed, we also did a little bit of exploration of printing at high resolution and printing some exotic materials. And one of the main motivations of us exploring into this micro extrusion was because we wanted to be able to print the micro heater we developed, and we're using high deck a lot, and it's not exactly cheap for prototyping purposes. For production, that might be a different story, but for prototyping, it's actually quite expensive. So we want to be able to print the micro heaters. This is one of the reasons why I developed this. And this is the printing stage we developed with the super high precision motors of 60 nanometer resolution with very fine nozzles, a single digit or some micron nozzle sizes. And with a pressure source of about 150 PSI from our lab to push the liquid out in order to print. So this is a constructed system, and this is the printing process. You can see this is a cooled glass, which forms a very fine nozzle to push the liquid out and to print. And we're able to achieve less than 10 micron printing resolution, and with a budget of less than $20,000, which would cost you about $100,000 if you buy it from the market. So this printing process, seems to be very simple because it's just a syringe you push out, you print. but it's actually quite complicated. It's very difficult to get a successful printing, and this is one of the reasons why we studied the fundamentals of this process and divided into 4 different phases. We developed equations to describe these different phases of printing and guide the printing process. Due to time, I'm not going to get into details of that, but we successfully printed some PDMS with a nozzle size of 2 micron and printing resolution of 5 micron. And we also expanded this micro extrusion printer into printing some optical materials. One of the things of printing optics is that it's very difficult to print glass because glass requires very high temperature to operate. So, and we looked to a material, the clear blister gel, which was a complete actually enforced miss. And we noticed this material to be very promising. So we developed a printer head to print this material with some heated chambers, and because it melts at only 100 C, so it's much more manageable. And we were able to print some patterns of these layers with this clear blister gel. But most interestingly was its optical properties. So we did some optical crystallization, and this is the refractive index of glass, and it's about 1.458. And this is the refractive index of a different grade of gel, and it's comparable or even a little bit larger than glass. In terms of optical transmittance, and the black line here is glass, okay, and it has about 90% of transmittance. And in the visible range, we can say our gel, the gel that we have here is this red line. It can actually surpass the optical transmittance of glass. So in the visible range, in the visible light range. So with that, we were able to build some waveguides to use this gel to show its optical potential. And the most important is flexible. So you can actually build optical circuits in 3D like this. And also build some cosmetic patterns with 3D structures like this. And optical circuits, splitter, we can split light into multiple bands and also combine lights into the single ones in 3D. We have also developed an optical encoder to show that it can be used to detect distance because it's using its waveguide properties, and by detecting by connecting the light source through the waveguide to the sensors. So that's some of the work we've been doing in the mechanical engineering, and I know I'm running a little bit out of time, and but if we have time, I would be happy to take any questions. Thank you all.